Yeah. Okay. So last time we started talking about the idea of risk minimization. So this is a more general, I would say, viewpoint on the prediction problem. So if you recall, we had this joint distribution for a pair x and y. So you want to predict basically y based on x, and so we have a known distribution. So in the local averaging sort of idea, or the first few lectures, we talked about how to estimate the conditional expectation of y given x. So conditional expectation is a function. So we can just say, let's say I want to learn a function of x that's approximately y. And to do this, I introduce a loss function on the space y cross y. This takes two values of y, let's say like the true y and then the estimated y, and then gives you like a measure of how bad you're doing, let's say. If you take the if you have the function, so we apply it to the x, that's our prediction of y, and then we compare it with y using the loss function here, and then we take the expectation as well. So now we have a deterministic quantity here, and this is sort of a measure of how well we are doing on average on a test point, right? So x and y, you can think of it as a new data point that you're seeing in the future from the same data set. And this is, let's say, prediction error, sometimes called generalization sort of error, or yeah, you can call it generalization error or prediction error, whatever you want. So how will you generalize to? How will you generalize to new data points? And so if you take the loss function to be the quadratic loss, then you'll show in your homework problems that if the loss is this quadratic loss, then the optimal solution, there's a unique solution to this, and that would be the regression function, basically. So if you've taken 200B with me, there's like a general result. This is, you can think of it as a Bayesian problem. And you can think of y as the unknown parameter, which we have put distribution on. And so this is a sort of Bayes risk. And this is the Bayes rule. And the Bayes rule can be obtained, you can easily show, by solving the problem that minimizes the posterior. So HSH star of x in general would be argmin. That this belongs to the argmin. Let's say y tilde, this is a generic point, expectation L of, or let's say y. This is y, and then y conditional on x. So you condition on x, this would be fixed. So now I have to determine what this fixed value is. And this is how you can minimize it. So if you minimize this sort of posterior risk, the solution by iterated expectation, the smoothing property, you can show that if hx minimizes this over all y for every x, basically if fxx, this is a number, the output, but because it depends on x, it would be a function of x. And so, so you can say the Bayes rule. This turns out to be the solution of the problem. So Bayes rule is the minimizer. Minimizer of the posterior risk. So here we're gonna talk about risk and like loss. There's like a difference in terminology. So here risk is like assuming y is unknown, the unknown parameter. So if you go back to 200B, the idea is there. So you can think of this as a parameter that we put a prior on, and then we had probability of x given y, basically, which is x given theta. That's the parametric model. And then this is a parameter we put a prior on. And then you define a joint distribution. Now you want to estimate the parameter given x, and this is the risk, Bayesian risk. And that's how you do it. But like in the prediction problems, there's another way that you can view it in the framework decision theory, which is more natural. I'll talk about it. But this is the solution. Okay? So this is just a way of obtaining the solution. Okay, so if you plug in the quadratic laws here, you can just solve, and this comes out. If you use just prove this for yourself, that this is the optimal solution. If you do the classification, the loss usually is taken to be the 0-1 loss. So y is binary, and so you pay a loss of 1 if you predict incorrectly. You pay a loss of 0 if you predict correctly. So this is a binary loss. And if I define the regression function here to be, let's say, eta, it's common sometimes to write it like that in this case. Because this is an indicator variable, this expectation is just the probability that y is equal to 1 given x. And then you can go and show that minimizing this basically equivalent to maximizing the posterior this probability. So if this probability is bigger than probability that y is equal to 0, you'd go with 1. If the other way, so if eta x is bigger than 1/2, means that the two probabilities here, probability that y is equal to 1 and y is equal to 0, they sum to 1. So if this is bigger than 1/2, this is bigger than the probability that y is equal to 0. So this is probability y for 1 given x is bigger than the probability that y equals 0 is bigger than x equal to x. And you can see from this, you do the calculation, that's exactly the case where you have to declare 1. And if it's less than 1/2, you do 0. And if it's 1/2, then you can pick it arbitrarily. So if eta x equal 1/2 has a non-trivial probability, then the optimal solution is not unique. So there are many versions of the Bayes rule. So it's sort of the optimal classifier. And you can see if I have, if you have an estimate of eta x, say eta hat x, I can define an estimator here by just plug in estimator. Let's say 1 if eta hat x is bigger than 1/2 or bigger than or equal to 1/2. 0 otherwise. So that's the plug-in estimator. We have the plug-in, that's a classifier. Right, so any regression estimate will give you the corresponding plug-in classifier. It might not be ideal because you're sort of expanding your samples to estimate this well everywhere, whereas for this you just need to figure out the regression function close to the boundary, and so you might use your samples more efficiently to just target that boundary instead of trying to. But for example, if you do KNN, right? So if you do the KNN regression estimate, in this case, you can see, roughly speaking, so this would be the KNN estimate for the regression function. In this case, would take the average, right, within the first k, the closest k neighbors, and because they're binary, so the average would be bigger than 1/2, right? So if this is the KNN estimator being bigger than 1/2 means more than half the points are 1 among the k nearest neighbors. So that's how you get the k nearest neighbor classifier. So you look at the k nearest neighbors and take the majority vote of the labels, basically. Okay, so the KNN regressor just plugging into this would give you the KNN classifier. And similarly for the other ones. So, and regressor, like eta hat x would give you the KNN classifier. H hat x, so on, etc. Questions? Okay, so as before, we have a training sample. These are IID from P. And then because we don't know P, we cannot compute any of these because they rely on the unknown distribution, the conditional distribution of y given x. So what we do is that we look at the empirical distribution of these points, which is something like that. So this is the measure that puts mass 1 at location xi, yi. So this is saying that we put mass 1 over n. So if I have a training point here, x1, y1, x2, y2, x3, y3. So we have a probability measure that puts mass 1 over n at each one of these points. So let's say these are coming out of the screen, right? 1 over n, like there are more points here, so there are n points. Xn, yn. And so this is a probability distribution on the space. Sometimes we call it Z, the joint is the space that the pair lives in. And what this is saying is that the probability assigned to any set here would be just you sum these weights that lie on that, or the weights of the points that lie inside that set. So so you know what this is. So Pn A would be just 1 over n summation I from 1 to n. How many xi, yi belong to A? So this is an estimator, like a non-parametric estimator of this. And if I replace this expectation here in the optimal solution by the expectation with respect to this guy, I would get this problem. Okay. So replacing the expectation with the empirical estimate, with the empirical expectation, I get a problem which is feasible. Now I can solve this because I get to see the training data points, I have the loss, and hopefully I can minimize over all functions. This is called empirical risk minimization. If you think of this as the risk, this is the empirical risk. A better name for it is a loss. I'll talk about it a little bit. But the problem is ill-posed. So this problem, there's a problem with this. What is the problem with this? Just minimize, let's say, over all functions. What would happen? Yeah, so because if I don't put any reasonable restriction on h, the natural function is just map xi to yi exactly and just arbitrarily do anything that you want. Outside, let's say L of x is the quadratic loss. The loss might not necessarily like penalize, but let's say for the quadratic loss, that's the best that you can do. So you just, so say for quadratic loss, also for 0, 1 loss, set hxi equal yi, and h of x, like yeah, okay, h of xi, or define h of x to be yi if x is equal xi, or I equal 1 to n, and arbitrarily otherwise. Okay, so there are many such functions. This is an example where you have like what is called overfitting. So you have overfitted to the training data. So you perfectly reconstruct the training data, but oftentimes when you do this, usually you're not going to do good on the future tests. So this function that I constructed, let's say, if I plug in into that, let's say expectation with respect to xy of h hat xi, sorry, h hat x minus y, this is in general going to be big. So there's going to be a problem with generalization, sort of. Anyone sees like, why would that be big? Let's say x is like continuous, like Gaussian, multivariate Gaussian. Right. What would happen here? So let's say I define it to be 0. So let's say h of x is y, I here, and 0 elsewhere. Right. So the way I'm going to do it is just here I'm going to define it to be yi. The rest is 0. What would this be? Yeah. So if this is like x is coming from a continuous distribution, h hat of x with probability 0 is going to be one of these points. So if it's 0 everywhere, this is like going to be, so if suppose I do it as so 0, then this would be just expectation of y squared. Okay, so you have it's as if you have like estimated the 0 function. So there's no sort of generalization here. Okay, so it's very simple to see that this is not going to work. So what should we do? Like the first simple step failed. Okay, great. Yeah. So the way that you do it is just put imposed restrictions. For example, if I assume that h is continuous, this would rule out this case. So I can't just arbitrarily define it everywhere if it's smooth. And so the idea is exactly that. So you put restriction on the class of functions. So let's say we pick a class of h of functions mapping from x to y and solve this empirical risk minimization over only this class. Now I'm going to call this h hat of n. This still could have like multiple solutions, but if I choose the class right, hopefully I'll avoid that issue of overfitting. So this is from this book by Shalev, Schwartz, and David. So by restricting the learner to choosing a predictor from H, we bias it towards a particular set of predictors. Such restrictions are often called an inductive bias. I just included it for this term because you might see it in the literature. It's not the usual statistics bias, but has the meaning of like forcing something to lie somewhere. So it's inductive. The reason why it's called inductive, sort of, I believe, is because it's determined before you see any data. Okay, so it's not imposed by the data, it's just coming from your prior knowledge. So it should ideally be based on some prior knowledge about the problem to be learned. Okay. So remember this traffic phrase, inductive bias. It's a machine learning term. It's not a statistics term. So questions? So some people, like for example, in this book, so you can call H a predictor or a hypothesis. Again, hypothesis is not something a statistician would call this, because it would get confused with the hypothesis testing sort of issue. But they call it a hypothesis because I would assume it's just, generally speaking, it's a candidate, let's say, for your classifier. I forgot exactly what they call it, like why they call it, but they call it hypothesis. And then H is called a hypothesis class. So H stands for hypothesis. A predictor is a better name. So it's a prediction problem, and this is a predictor. But just two questions. So this is the general framework. It's like going to occupy a lot of the things that we talk about. It's fairly general, you can see, and you can, by varying the loss function and varying this class H, you can get all sorts of estimators, all sorts of problems you can try to solve. For example, linear regression, here are some examples, correspond to this linear class. So the functions that look like theta transpose times x for some theta in RD. Let's say x is a subset of RD. Subset of RD. Okay, and then we have partitioning estimators. So the partitioning estimators that we talked about are an example of this. How they're an example, you can think of the, so suppose I have, so this function, I'm going to try to estimate, I want to try to estimate it. What I'm doing is I'm basically partitioning this space into, let's say this is 0, 1, into a bunch of bins, let's say equally size bins. And then I'm going to approximate this by like the average here, right? So that's what the partitioning estimator is going to do. You can see that you can easily show for yourself that this is equivalent to minimizing that empirical loss over the class of piecewise constant functions over the cells of this fixed partition. So all the functions that I'm going to look at are going to be everything that's fixed on these partitions. So this is another one. This is another one. Right, so it could be like that. So every function that's piecewise constant over these cells of the partition, that would include my class of functions. So it's a, is it an infinite dimensional class, finite dimensional class? Finite dimensional, yeah. So the basis would be like 1 here and then 0 elsewhere, 1 here and 0 elsewhere, and it's just the dimension would be the number of cells of the partition. And then you can see that if you minimize this cost function, let's say with the L2 quadratic loss, this is the piecewise constant over the cells, this is quadratic loss. The best in each, like these, the values over these partitions are independently determined, and this has to be like the average of the points there. This is not like not the average of the function, but the average of the points. So you get training points here. The thing that I wrote is like the population version, the one with the expectation, the true expectation. Okay, so partitioning estimators are an example. So this would be like a finite dimensional function of space in general. Decision trees are an example. So do people know what decision trees are? What is a decision tree? Let's say in 2 dimensions, let's say X is 2-dimensional. What would a decision tree, like the class of functions? Yeah, but it's like a very particular way of choosing the cells of the partition. So what you'd look at, let's say I have x1 and x2. Let's say you're in R2. X is a subset of R2. What you do is like, if you've seen how they train the decision trees, let's say you're looking at 0, 1. You pick the first coordinate, and you find a location here that if you split, the values of y would be like the least variable within each cell. So they call it like purity or impurity. The impurity is small. So if you're doing regression, the variance of the values of y within the pieces are minimized. So for example, I'll split at this point. And then you also do it, the optimal split, find it at this point, and then pick whichever gives you the smallest total like variance. So it might be that I have to like split this first. If I do it this, you do it one at a time. So you do something like this. And so the function is supposed to be at this point constant here and constant there. Then you'd go one level further, and then now again you consider whether you have to split along this direction and along this direction within each of these. So within this, it might be that I have to split. It's best to split here. Within this, it might be that I have to split again on this coordinate. Okay, and then within each one of them, again, you do, for example, this might be like that. Here I might do like this and this. So in each cell, you decide whether each one of the coordinates and the location. So the location is adaptive, and in the end, you'd get a function which is going to be piecewise constant on these cells. So the cells are adaptively selected. The way you do it is in practice in a greedy fashion, but you can think of all the possible cells that look like this. Okay, all the cells that you can get from this binary type division, and the location is also a parameter. Okay, so this, for example, a pattern, and these split points are also parameters. If I split in a different fashion, I split, for example, first along x1, and then each one again along x1. And for example, I could do something like this. I could first, let's say, split along x1 at this point, and then again along x1, and then in each one I'll do along x2, for example. This is another type of partition, and then location of these could also vary. So this, if you think of this, this defines, depending on the depth of the tree, the depth could also be part of the parameters. So you get a function class, and you can try to minimize over this function class. And decision theory, the algorithm that's used in practice, is a greedy way of fitting this to this piecewise set of functions over these cells. It might not give you the optimal partitioning. So the optimal partitioning, it's empty hard to find the optimal thing, because you have to. If I choose the first one greedily, it might change the subsequent one. So you have to search over all possible ways of splitting, which is generally not. You can count how many ways it is, and it's combinatorial. So decision theories are an example. At least the global solution. Neural networks are another example. This is quite simple. Let's say something like the simplest thing is it's like a linear function there, but you would have also a nonlinearity. So it's the class of functions that look like this for some theta in R. There's also an intercept that you can absorb. The functions that look like this, this nonlinearity is what makes it interesting. And then you compose these as well. So this and the compositions of it in different fashions. So it's a natural class of functions. Banach-Hilbert spaces. These are infinite dimensional. So like LPS spaces, the space of continuous function in compact support solver spaces. And specific case of this, which we talked about, is this class of reproducing kernel Hilbert spaces, which are very suitable for the ERM business. So I'm going to talk about that. It's a special kind of Hilbert space in which evaluation functional behaves nicely. And then, so in these spaces, usually you specify a basis, and then you can treat the problem as the function being linear sort of in that basis, at least in the Hilbert spaces. This is like an infinite dimensional analog. So if I define a basis function, for example, for the L2, I could pick a basis. So these functions are my basis. And then I can write any function in the L2 as like theta j by jx, j from 1 to infinity. And then I put some restrictions on theta. Theta equal theta j has some restrictions. you can imagine without any restrictions on theta, this space is too big. And usually it overfit. But I can impose some conditions. So for example, I can assume that the thetas like drop like fast. And this situation is exactly what happens with the RKHS. So we'll see that. So the idea of basis expansion. And then we have sieves that are like finite families of functions. Usually you change the number of functions as your sample size grows. So if you look at finite families, you usually don't overfit on finite families if the number is small. But as you get more and more samples, you can increase the number. And usually they're easy to analyze. They might be very difficult to like implement in practice, but they're usually a theoretical device. So you can approximate a lot of these cases by these sieves or families of functions that are finite, and then approach the entire class as you increase n. Okay, so it's fairly general. The setting is fairly general. There are other things that you can think of that you can write in this fashion, but basically, I would say almost any estimator that you can think of can be sort of cast in this fashion, sort of. Questions? Okay, so how do we measure the performance now? So we have this estimator. We would like to compare it to the optimal one, the H star, right? So again, now I'm going to, let's say, introduce some notation. So this is the measure of performance that we're looking at. You can call it the prediction loss. People usually call it risk, but from a decision theoretic perspective, this looks like a loss. And it's a form of a loss between the function and the probability distribution. So if I input a probability distribution on the pair xy, which we call z, and if I have a candidate function, this would give me a deterministic value. So this is how well this function is doing on that distribution. Okay, I'm predicting from that distribution. So it's like, again, if you have seen 200b, this is like our parameter, which is now an infinite dimensional object. And this is like the estimate. So it's like in decision theory, you're like, this is like action. This is action. This is action. This is the parameter. Okay, so the action and parameter need not be the same. So in decision theory, you're like, you have a parameter, you observe data from a model like probability distribution parameterized by that parameter, and then you take an action and then you pay a loss. This is like, you have this distribution on the data, we observe the data and we take this action and we pay this loss. Okay. And the loss is, in this case, prediction loss, but it fits within the general, so like the action here in decision theory. It should be like the other way around. Usually you put the parameter first and the action second, but it's fine in this case. So if you think it that way, this is the loss from a decision theoretic perspective. There's also a risk, which is like the expectation of this guy. But let's forget about this for now. So what we care about is now, if I have a prediction rule, let's say the RM, I can apply this loss on it and see how well I'm doing. Right? So this is the prediction performance or the prediction loss of that. And if you have universal consistency, this converges to the loss of H star, which is the optimal predictor, the minimizer of this basically. And we want this to hold over all P, or like sufficiently general class of P. So that's the idea of universal consistency translated to this setting. Sounds good? So it's just saying that you can think of it as generalization error of this is converging to the optimal generalization error. So I'm gonna, for the future, drop the P. I'm just gonna write L of H. This is again a deterministic quantity, which is performance on a future test point, averaged out over the future test point. There is this excess loss. Some people call it excess risk because they call this a risk. So this is L of H minus L of H star. So the difference of these two, we call it the excess risk or loss. And the prediction consistency is basically saying that this excess risk of H hat n converges in probability to 0. Okay, so the excess risk is useful because it can go to 0. This prediction loss or risk cannot go to 0. There's like a minimum possible. You can't improve beyond the optimal, let's say, classifier or the optimal predictor. Okay, so far so good. Just a bunch of notations. Okay, a little bit more on the notation. So one issue is, like in the ERM, this is a minimizer of the empirical loss over class H. This need not be in the class H. Okay, and then you can imagine that this is probably not going to happen. If this is a statement in that class, this is outside that class. It's very unlikely, unless the problem has a very specific case where the losses of the functions in the H can be like reproduced, like the losses of functions in the H can reproduce all possible losses. This is not going to happen generally. So what happens instead is we can decompose the risk a little bit further for the loss. In general, H star might not be in H. Let H star H be the minimizer of the, let's call it population loss or the prediction loss over H. So this is the best within that class I can get if I had like infinite sample size. And then we can look at this restricted excess loss, or you can call it the estimation error if you want, which is the loss minus the loss of the best in class H. So LH minus the infimum now over all the functions in H. And usually what we want is this excess restricted excess loss or estimation error to go to 0, okay, in probability. And ideally we want to characterize how fast it goes to 0. And we'll see rates depend on the sample size and also a notion of the size of the function class. And then we have this decomposition that, so if you recall, this is just LH minus L of H star, the global optimal. I'm writing it as LH minus L of H star H. This is the restricted thing. And then you can see adding and subtracting these basically, and this guy. So this is the difference between the loss of the best in class and the global best. So you can call this the approximation error. This is a deterministic quantity. There's no randomness in this. And this depends on how well the class of functions can approximate your true function, right? So this is class H, and this is H star. In general, like H star H would be like usually at the boundary. There is like some error here. That's the approximation error. This is the estimation error. So we're going to focus on this to let this go to 0, and like prove that this goes to 0. This part like requires a separate sort of argument. You can also sort of try to control that and then balance out the two. So generally what happens is when H gets large, the larger it gets, this, what happens to this? What happens to this? When H, the function class becomes bigger, this goes down, yeah, because let's say classes are nested. This is guaranteed to get smaller, and this is the smallest possible. So this goes down. This generally goes up because we are optimizing over a bigger class. We're optimizing over a bigger class. We have better potential to overfit. So this is going to try to like approximate yi very closely, and so you introduce more noise. So the estimation error goes up. So there's this trade-off. If I increase the size of H, I increase the estimation error, decrease the approximation error, vice versa. If I decrease the size of edge, this goes down, this goes up. So you try to do a balance. This is like the classical bias variance trade-off that you saw, but this is like a little bit more general. And you can think of whether this is related to bias variance decomposition in the quadratic case or not. That's something that's worth thinking about. Okay, so we have this approximation, estimation, error, decomposition. And basically the two pieces are analyzed separate using separate tools. We're going to focus on the estimation error, okay? And try to get it to go to 0 for progressively bigger classes of functions. And at some point you'd be happy to say, okay, this class is big enough, probably this is small enough. Or you can like separately argue exactly how fast this is going to 0. For sieves, for example, there's the number. And as you increase the number, you can control how this behaves and how this behaves, and then try to balance the two off. Questions? So a lot of notations, but hopefully you get comfortable with this. Can now move on. Any questions about this? Okay, I just want to mention this idea of pack learning or pack learnability, agnostic pack learning. The book that I cited from, for example, say ML people usually like view the problem in this fashion, which is very close. I just wanted to point out the similarities in case you encounter this. So the notion is pack learnability. In particular, the version that I'm talking about, they call it agnostic pack learnability. So hypothesis class H is called agnostic pack learnable with respect to the loss function, like the underlying spaces, things like this. If there exists a function, this is called the sample complexity, the function of epsilon and delta. This is an integer, let's say, a potential sample size. And a learning algorithm, there's a learning algorithm such that for every epsilon and delta in 0 to 1, and every distribution p on that underlying space, the estimates that this learning algorithm produces based on an ID sample size and at least this much satisfy this inequality, which is saying that the excess risk within that class of that estimator is less than epsilon with probability at least 1 minus delta. And the probability is taken, I've written it like this to emphasize under the randomness in this ID sample size n. Okay, so the only randomness is in this, and this is dependent on dn, the sample size. So this is like h hat n. You can think of h hat n both as the estimator as the rule. So it's like the rule applied to this would be the estimator, and the randomness in this is just described by the distribution, which is the product of these n times. So this is saying that probability at least 1 minus delta, this is less than or equal to epsilon. This is very much like the consistency that I mentioned. So if you unpack this, this is saying that the probability that this is bigger than epsilon is going to 0. This is saying exactly the same thing, but this is more quantitative. Let's say you can specify a given epsilon and a given delta, and then it gives you a sample size, how big I should be. If you rearrange it, this is bigger than epsilon is less than delta, which is exactly like the formulation of the consistency. So I would say this is like a quantitative form of convergence probability. The reason why it's called PAC, it stands for probably approximately correct. Probably means we let the slack be there. So probably correct. There's a probability that it's not correct. Approximately means approximately, so this is not going to be 0, just up to epsilon. And the agnostic part is related to something about the fact that the true function that so there's basically noise, and this cannot go to like this can't be. So there's nothing that has like excess risk 0, and basically sort of agnostic means that like the general pack learning. It's not like a, so pack learnable. I understand correctly, roughly means that H star belongs to H, which we're not assuming here. And also this guy is 0, at least in the classification case. This would imply in the classification case that y is exactly H star x with probability 1. So there is a function that exactly generates the relation between x star and x and y. So there's no noise, and so it's a simplified version of this. But let's stick with this for now. Maybe come back to that later. If you're interested, you can look at that book for the definition of packed learnable. This is a more general version. And this is, as I mentioned, called sample complexity, and sort of tells you how much sample, like what is the sample size required to achieve this guarantee. Questions? Okay, just another set of notations. A summary of the notation. So population loss and risk is this guy. You're going to also introduce this notation for simplicity LH of Z, which is this guy. Okay, so it's like a loss between H and Z. And then if I introduce it, I can just simply write it that way. And this, I'm going to look at the empirical loss. This is the notation for the empirical loss. And this is also written like this with that notation. And then the RM estimator just minimizes this over class H. And you want to control the estimation error, which is this loss of this minus the best in class. Okay. So the new notation is this empirical loss and empirical risk. Okay, so it's a lot of setup, but any questions? Okay, so let's now see a result. So the first thing that we can do is to look at finite classes of functions. And this is a result. If Hn, well, let Hn be the ERM, empirical risk minimizer, and let the loss be B bounded. What I mean by B bounded is the values are between 0 and B. For example, classification with 0, 1 loss satisfies this clearly. Regression, let's say on a bounded domain, would satisfy this, like if X is bounded. Unbounded domain, this doesn't hold. And then the function class is finite. Then I have this result with probability 1 minus delta. I get that the excess risk of the ERM is controlled like this, and you can see there are some components here. There is the cardinality of the set H. This is how many functions are in H. And then that appears as a log. So if you ignore the constants and delta, this is like up to constant, it's like root log cardinality of H divided by n. So if the cardinality of H is finite, this is going like 1 over root n to 0. So even if H is going to infinity, the cardinality, you can see that if the log H divided by n goes to 0, we still have a consistent sort of estimator. So in terms of the packed learnability, this you translate this to packed learnability by, let's say, letting this be less than or equal to epsilon. I want this to be less than or equal to epsilon, and then you can invert it. This would mean that 2b log 2h divided by delta divided by n is less than or equal to epsilon, right? And then I move the epsilon here, or say epsilon squared. And then you move epsilon there, so 2b log 2h over delta divided by epsilon squared bigger than n. So n has to be bigger than this. So if you take the ceiling, because this might not be an integer, so if I take the ceiling, I can take the sample complexity to be this, at least this much. So we know that the optimal sample complexity has to, like, can be at most this, as I can achieve. So that gives you that the finite classes are agnostic packed learnable with this sample complexity. So this is going down like 1 over root n, or in this case, the complexity is like 1 over epsilon squared. That's the equivalent statement. Okay, sounds good. So how do we prove something like this? Let's see if you guys can help me prove this. So you can see Hoffman's inequality. There is like a concentration inequality involved. Have you guys seen concentration inequality? Okay, so how do we show this? Epsilon h, hn is, this is L h hat n minus, let's call it L h star h, that's the best in class h, that's what we have, right? And I also know that h hat n is argument 1 over n summation I from 1 to n. Let's not do it that way. Argument just ln h in h. Okay, it's the minimizer of the empirical loss. This is the empirical loss. This is the population or the infinite sample size loss. It's prediction loss. So how do we relate this to that? Anyone recalls like 200B if you have taken the technique that we use usually for consistency? So like so-called basic inequality argument. So this is an optimal for a problem. So we can use like 0 order optimality. You recall? So Ln h hat n is less than or equal to Ln h for any h in the class. In particular, h star h is in the class. So the empirical loss of the ERM is going to be less than or equal to the empirical loss of the best in class. Right? So now they rearrange this. This is telling me h star h minus ln h hat n is bigger than or equal to 0. Right? Now I can add this because it's bigger than or equal to 0. Add this to this, and I get an upper bound. I'm going to add it to that, and you can see why I want to do that. So if I add it to that, I get this, and I'm gonna like put this term first, minus ln h hat n, and then the other term plus ln h star h minus l h star h. Let's see, that's the l h star h. Okay. Does that make sense? I just added this, which is bigger than 0, so I get an upper bound on the excess risk. So now what is the next step? The way I did this, I have like created this deviation of ln minus l at this function, and also ln minus l at this function. So ln is the empirical loss of converging to the true loss pointwise. So ln h, if you recall, this is ln h. If you fix the h, this is going to be a set of IID random variables. By the law of large numbers, this converges to that in probability or almost surely for any fixed x. for any fixed h. Okay, so pointwise these ln h is converging. So ln h, ln converges to, let's say, L, probably pointwise. So for this, for example, because I've evaluated a fixed function, I can conclude that this is converging to 0 in probability. This is fine. However, this one is problematic. You remember why this is problematic? I can't use the law of large numbers on this. H hat n varies, and worse, H hat n is dependent on ln as well. It's like evaluating the random function at a random point which depends on the function and also varies. So the law of large number here is not useful, not immediately. So what is the solution? Anyone remembers from 200B? How can I bound this by something? Just get rid of the varying argument. Let's call this basic inequality. This would be bounded by, let's say, ln h minus lh, absolute value supremum h in h. Okay. Bounded by this. This term is also bounded by that, because both h hat n and this are there, so this is going to be twice there. Okay. This is a uniform sort of quantity. You can think of it as, well, we usually do like a uniform norm. So if you think of these as functions, this is the sup norm, basically, of the loss function. So I usually write it as, I might write it as this, h. This is just a notation. So this is bounded by twice this for simplicity. So the uniform norm of this deviation over the entire function class. Okay, so if you do this, it's a big jump, but if I can control this uniform norm, and I know that there's no randomness here except the ln, so we got rid of the issue that this is a value at the random point. So if I can control this, I can definitely control this, and so on. The problem reduces to this. So this is an example where I want to show that this conversion probably to 0. This is called the uniform law of large numbers. Okay, because convergence is now uniform. It's in the sup norm rather than pointwise. The question is that does this hold? In order to do so, we need some sort of a quantitative version of the law of large numbers. Actually, this holds because h is finite. You don't even need to do. It just follows from the law of large numbers because h is finite. But I want to like also get the rate. So we'll do the Haftin's inequality. Okay, so Haftin's inequality says that if xi's are independent random variables, xi's are in ai and bi almost surely, and then you look at the average has this concentration. I've rewritten it in this fashion. It's an exponential concentration. So for example, if xi's are in 0 to b, then these would all be like b squared. And so you'd get just 2n t squared b squared. And so if you look at ln is an example of this. So ln of h is just summation sum from 1 to n in the notation lh of zi. And L of x, so L of h is basically the expectation of ln of h. If you do it, you'd get just the expectation of, let's say, L h z1, which is exactly what L is. So what this is saying is that the probability that ln h minus LH, and L is at B bounded. So the probability that this is bigger than T is less than exactly 2 x negative 2nt squared over B squared. Okay. Cut. Paste. That's the result that I have from Hoffman. This holds for any fixed function. So how do I get the bound that I want uniformly? So I want now the probability, this holds for all h in h or otherwise actually. So the probability that sup h in h is ln h minus lh bigger than t. How can I bound this now? So the supremum being bigger than t means that at least one of these is bigger than t, which means it's the union of these events, right? So this is the same as the union over h of ln h minus L of h bigger than t. What can I use here? Union bound, yeah, union bound. So this is bounded by summation I from 1 to, not I from 1 to, it's just h in h, probability that ln h minus lh is bigger than t. It's going to be bounded, all of them are bounded by the same quantity. So I get the cardinality of h times 2 times e to the negative 2nt squared b squared. Okay, we're almost done. Now at this point I want, so the e, so what I want to do is, let's say I want to make this probability be less than delta, okay? Which means that 2h delta has to be less than e to the 2nt squared. E squared, take the log, get log 2h delta, and then move b to the other side, less than or equal to b squared divided by 2. Okay. Where is, yeah, fine. E squared divided by 2n. If I take the log and then move e squared divided by 2n, okay, that's that. And so I take a square root, I get this. So t has to be this. I just take t to be as small as possible. So I'm just going to take t to be, take it to be equal to this. If I take t to be equal to this, I've shown that p is ln minus l f bigger than root, or it's like less than or equal to root e2 2n log 2h divided by delta is bigger than 1 minus delta. And then if I multiply by 2, because this is bounded by 2, if I multiply by 2, I get the same thing for the excess risk. And if you do it, it's just there. Okay, so that just completes the proof. There's just an application of the union bound, and then you choose the t properly so that the other side is bounded by delta, and then you're done. Okay, so basic inequality and then a uniform convergence. Okay, so let's stop here.